All right. Good morning, Prince, Neo, Trisha, and Denmark. So for today, we'll quickly recall what we did last time, and then I'll present to you the code that I used to present the simulation na pinakita ko towards the end of the last lecture, ano? And I'm thinking of giving you the second problem set, ano? So may naisip na akong problem kanina while I was revisiting the Matlab code that I used. So okay, but before that, I already uploaded homework number 5 kagabi, which is the recitation question that I am asking you last time kung bakit nagme-make sense na pumapangit yung prediction to the temperature as we go forward in time, right? Because remember, at time t equals 0, we know the exact temperature profile on the entire rod because that is given by the initial condition. Tapos nung ginawa natin yung method, yung discretization method natin, yung prediction para kay U upper 1, okay, which is basically the matrix A times U upper 0 plus V upper 0, nakakuha tayo ng super gandang approximation that you have seen in the animation last time. Pero as we go forward, pag habang lumalaki na yung time step natin, so nakailang delta t na tayo na step in time, pataas ng pataas yung error. I think when we reach t equals 1, which is about 120 times steps from t sub 0 equals 0, nasa around 4% na. Pero nung simula, ang ganda ng profile. It's about less than 1% actually yung error. So the question I posted was, bakit kaya ganon? Or why do you think na pumapangit yung approximation? Though hindi ganun kapangit, ano? Kasi nasa below 5% pa rin naman siya after 120 or 121 times steps. But the question is, can you hypothesize why it happens? Ano? It could be traced back when you go to the formula. I think we have formula, yeah, this formula. So coming from this formula, why do you think that will naturally occur? Or that it should have been expected that even if everything will go on as expected, dapat ma-anticipate pa rin natin na magkakaroon tayo ng error or the piling up of errors as we go forward in time. All right? So that's your homework number 5. I promise the deadline is on Monday right before midnight. But since late question upload, so the deadline for homework number 5 would be 11:59. Will be 9:59 a.m. on Tuesday. All right? So bago kayo mag-login sa Teams for our class on Tuesday, make sure to have submitted homework number 5 kasi explain ko na yung reason kung bakit dapat siya expected during the class. All right? Doon ko sisimulan yung klase sa Tuesday. All right? The questionnaire is already in Canvas, so you can go ahead and read it, right? Hold on, guys. Okay, so let's just quickly recall what we are trying to solve, and then I'll switch to my MATLAB code. So the inverse problem that we are solving last time still involves the heat equation, all right? But formally speaking, it is about finding the initial condition. Finding the initial condition, f, all right, which is a function. Basically, we can say it's at least a continuous function on the interval 0 to, initial condition to, no? Oh, yeah. It should be from 0 to L on the interval of consideration. Kasi f is a function of space, right? It's the initial condition. So this is the temperature profile when t is equal to 0. You can think of f to be u evaluated at all x's at time t equals 0. Ito yung gusto nating hanapin. What is the time profile, what is the temperature profile in the rod at the beginning of the experiment? So we want to find f, which is a continuous function from 0 to L, such that the solution of the heat equation, So, ito yung heat equation na tinatry nating isolve. Partial derivative with respect to time ni u at xt is equal to constant d. But in this particular case, my constant d is equal to 1 times the second partial with respect to space of u xt. And then we're also given the boundary conditions. So we have u of 0t and u of lt is equal to 0 for all t greater than 0. And the desired initial condition that u of x0 equals f of x for all x in the open interval 0 to L satisfies u of x comma 1, right? So, hold on. Excuse me, guys, again. Okay, so ito yung specific problem na sinimulate ko towards the end of the lecture last time. So we're looking for the initial condition, kaya siya inverse problem, right? In a forward problem, we know all the boundary and the initial conditions. In the inverse problem, pabaliktad. Ang hinahanap ko naman ay yung initial condition, tapos alam ko yung temperature profile at the terminal time. In this particular case, the terminal time that I'm using is t equals 1. Right? So that's why I want to find what should be the data to the governing law, basically what is the initial condition, such that the solution to this PDE system, so you have the heat equation, you have the boundary condition, which is given, then you have the initial condition, which is unknown. I want that the solution to this PDE should satisfy a certain temperature profile at T equals 1. All right? So, ito naman yung input doon sa ating inverse problem, which is basically the output kung forward problem yung sinosolve natin. So, gusto ko makita ano dapat si f, ano si little f, such that yung u of x1 ay ma-force to be 10 sine 2x. Sorry, not 10 sine 2x. Ang gusto kong solution ay 10 e to the negative 4 sine 2x. All right? Because remember, this is basically I'm trying to solve backwards yung binigay ko sa inyo sa homework. I think it's homework 2, if I'm not mistaken. Remember, meron tayong example ng isang PDE with an exact solution. And that is, lagi ko siyang hinahanap. Yeah, there we go. So, ito yung ginawa nyo in one of the homeworks. Pinakita nyo na etong PDE na to has the following solution. 10 e to the negative 40 sine 2x. So the forward problem, you know everything. Okay? Then what we want to find is this. The temperature profile at an arbitrary time, capital T. Now, sa inverse problem, baliktad. Alam natin ano yung target temperature natin after 1 second. So we know the exact solution. Plug in T equals 1. So I have 10 e to the negative 4 sine 2x. So that would be my target temperature after 1 second. So the question is, what should be the initial temperature profile dun sa rod para after 1 second, yung temperature dun sa rod ay magpa-follow ng function 10 e to the negative 4 times sine 2x. Now we know the exact solution here. So from our analysis before, a solution to this inverse problem is f of x equals 10 sine 2x, right? So ito yung target nating i-reconstruct. Now, in real life, of course, you will not have data or you will not have access to the exact solution, all right? Kasi bakit ka pa bakit ka pa mag-numerical solution kung alam mo naman yung exact solution, right? But if you're writing a program, you're designing something to really solve a real life application, okay na nagsisimula ka sa isang sanity check. Meaning you are checking the robustness of your program or also of your numerical framework against known data. So parang ito yung model validation. So sa mga applied math, pag nagmo-model kayo, gagawa kayo ng equation that will supposedly explain a certain phenomenon. But if you want to validate the accuracy of your model or the efficacy of your model, i-compare mo yung prediction ng model mo sa isang known and established scenario, right? So, kailangan mo siyang i-run o i-simulate yung model mo using known parameters na alam mo kung ano yung gusto mong i-match. Isa yung paraan para ma-check yung robustness ng iyong program or ng iyong numerical framework against various non-theoretical aspects. Right? Like halimbawa, stability, numerical error propagation, truncation error, and so on. Kaya crucial na first step yung pag-validate ng solution. Alright? At yun yung ginagawa natin dito. Kasi iraran natin yung aking solution approach, okay? And I will try to recreate a known function or I will recreate a known scenario na alam na natin na para ma-achieve yung temperature na 10 e to the negative 4 sine 2x after 1 second, alam natin na one way to do so is to have initial temperature 10 sine 2x all throughout the rod. Now, can we recover f in our program or in our approach? That's something that we need to see. All right. Now, the solution approach that we tried is what we derive. Is it last time or right before we go to the reading break? But essentially, the discretized solution that we think of is an iterative one. So we iterate along the time domain. So we have u upper j equals A inverse times U upper J plus 1 minus V upper J, okay? And we start from J equals N all the way back to J equals 0, right? Ito yung target natin, right? So, because we know, so we are given, since we are given U of N plus 1, or U upper N plus 1, which is basically the temperature profile of the entire rod at time T sub N plus 1, where T sub N plus 1 is equal to 1, or terminal time. So given sa atin yung U sub N plus 1, so pwede ko itong gamitin in place of this quantity here or this vector here. So I'll be using J equals capital N, all right? V upper N is also known because this depends on the boundary conditions, okay? So that means if J is equal to N, if we plug in all those known information into this equation, we're going to get U upper N, which is basically the temperature profile one step backward. So it's going to be 1 minus delta T. So nakabalik na tayo na recover natin yung temperature profile one step backward in time. Now, and then we iterate. Kapag ang n na natin ay n minus 1, so this will be u upper n minus v upper n minus 1, and we will get u upper n minus 1, which is basically the the temperature profile 2 steps backward in time. Okay, and we try to do it as many times as needed hanggang makarating tayo sa t sub 0. So essentially, the final output here after iterating backward in time ay magiging U upper 0. Yan yung gusto nating marating. Because U upper 0 will give us really the temperature profile at the discretization points in the rod at time t equals 0. Yun yung tinatry kong i-simulate or i-generate using the Matlab code that I showed you last time. Okay? So I hope this framework is okay, yung mathematical framework. Any questions before I move to the Matlab code? Okay, so if there are none, let me shift screens. Okay, so I hope by now you're seeing my Matlab screen. I already shared the code with you. In-update ko yung heat diffusion.m dun sa module. I think it's module number 4, the latest module that we have. So you can download it. Medyo mas mahaba na ngayon yung program. So may dalawang parts na yung program, or actually 3 parts. First, we do have the problem initialization part. So that's lines 5 hanggang basically 49. So kasama na rito yung pag-develop ng matrix capital A together with the initial and the boundary conditions. So if you'll be using this program, tapos meron ako sa inyong ibang ipapagawa, papalitan nyo lang itong problem parameters. So you have the length of the rod, the terminal time, the constant capital D in the formula that we have for the PDE. All right. So again, nandito kay D, nakadepende yan dun sa material composition ng ating rod. And then F, G, and H are the initial, left, and the right boundary conditions respectively. So you just alter this if you need to run something aside from the specific example that we are solving. Tapos through FT, this is just the actual solution. Okay, so 10 e to the negative 40 sine 2x, this is the solution to the PDE. Again, in the real world, you might not have any access to line 15. So, kaya lang natin to ginagamit again para ma-validate yung result ng ating program and see what are the possible problems that we will encounter. Kasi parang ang perfect nung ginawa natin ngayon, ano, especially the forward problem solver, because we did a thorough analysis of it. So nakita natin na okay, magko-converge yung method. Sure tayo na magko-converge yung method at least on paper when delta t over delta x quantity squared is less than 1/2. And that's the reason why I chose the combo m equals 10 and n equals 120. Kasi sure ako dyan, yung delta t over delta x squared ay mas maliit sa 1/2. Okay? Now, that's on theory. That's on paper. All right? Kaya lang, I hope you realize this in AMAT 152 or ngayon na-realize nyo sa 174 na yung methods nating dinidesign on paper ay okay, that's fine. Pero once na ipagawa natin siya sa computers, iba na yung usapan. Kasi may additional driving force or may certain other forces that are working once we put the computations to the hands of a computer. All right? Kasi ang computers, finite machines yan. Hindi nila kayang isolve ang isang problem always exactly. So halimbawa, nagpo-compute ka ng 1/3 sa kanya. Alam natin, on paper, 1/3 is 1/3, right? It's 1 divided by 3, it's 0.3, so it's 0.3 followed by infinitely many 3's, right? Kaya lang, pag sa computer na yan, hindi niya i-store na 0.33333 and so on. Sulat niya lang yan na 0.3 followed by 16 other more 3's, alright? Kasi ang precision ng ating computers ay, say, 16 decimal digits. So hanggang ganun niya lang kayang i-store yung value. So meron ka ng truncation error na wala on paper. Kasi when you design 1/3 on paper, you are getting the exact quotient of 1/3. Pero kapag ka ginawa mo na yan sa computer, ang gagawin ni computer, puputulin niya yon up to the number of significant digits allowed in the memory. Okay? So kaya maganda rin na talagang tinetest mo yung program para sa yung numerical method mo, especially if you're doing it using a computer. Okay? All right. So yeah, ito yung mga medyo kailangan yung baguhin. And then line 28, ginawa niya lang yung discretization, including the representation for the PDE. So yung continuous model natin, which is a partial differential equation, now is reduced to a linear equation. Kasi ang kagandahan yung PDE, linear operator yon. So dahil linear operator siya, kaya natin siyang i-approximate using a linear system. And this is how I wrote the matrix A, right? Remember, yung matrix A, tri-diagonal yon. Sa diagonals niya, ang laman niya ay 1 minus 2D. Dun sa diagonal sa ibabaw at sa ilalim ng main diagonal, ang value naman niya ay little d. Right? And then si line 51 until line 128, siya yung para sa forward problem, right? I could have written a separate program for the forward problem. Okay, ngayon ko lang siya naisip. Pwede kong i-copy paste yung lines 1 hanggang 128 to another .m file para magkahiwalay. Pero ayoko nagbubukas ng super daming programs, ano. So kaya ang ginagawa ko, pagka gusto ko yung forward problem, i-uncomment ko lang yung lines 1 to 120, i-uncomment ko lang yung hanggang line 128. Pero dahil ngayon, inverse problem yung gusto nating gawin, so I'll be working with lines 130 hanggang sa dulo. Kung forward problem yung ipapagawa ko sa inyo, syempre, i-comment nyo itong lines 130 pababa. Madali lang naman mag-comment kay Matlab. You can highlight the portion that you want to be commented out. Tapos dito sa editor, meron ditong yung what do you call this? Itong percent symbol. Pag kinlik nyo yan, magiging comments na yung highlighted portion. Or you could press Control R in your keyboards. Okay? So, but let's see how the inverse problem solver is carried out in this program. Saglit lang, guys. All right. So, line 132, kailangan kong i-initialize yung data. All right. So, ito yung supposedly makukuha nyo from real life measurements. So, this is the true data, which is basically I am plugging in the discretization values for x. So, kukunin ko si x-vals. Si x-vals, ito yung x sub 0, ito si x sub 1, x sub 2, x sub 3, x sub 4, hanggang kay x sub m. So, ito yung mga discretization points in the open interval 0 to L. In this particular case, ang 0 to L natin ay 0 to pi. So, ito ay yung delta x, 2 delta x, 3 delta x, hanggang makarating kayo kay pi minus delta x. Okay? Pinlagin ko siya dun sa true solution kay capital T or the true terminal solution para makuha ko yung ating data. Right? So this is simulated data or this is the perfect data or the exact data na gusto nating temperature profile. Now, in real life, this could be something that you measure in time. Halimbawa, gusto mong i-trace yung historical temperature. So, kukuha ka ngayon ng temperature readings at this particular moment in time using some fancy thermometer or what. Tapos, yun yung gagamitin mong input dun sa equation na sinulat ko kanina. Yung U upper J equals A inverse U upper J plus 1 minus V upper J. Okay? So, ito yung gagawin nating right-hand side nun. Now, we will be considering a perfect data. So, wala munang noise. So, ang noise ko muna ay 0. Tapos, ang true data, i-assign ko siya dito sa matrix na to. U inverse is, o yung pang n plus 1 na column ni U inverse or ni U inv ay yung true data. I-store ko kasi yung mga temperature readings ko sa matrix na tatawagin kong U inverse. Bawat column ni U inverse would be the temperature profile of the discretization points in the rod at various time steps. So yung pinakadulong column ni U inverse, mga temperature yon at the terminal time, which is what we wanted to match. Okay? So kaya i-assign ko lang siya dito. Tapos, remember dun sa formula natin, involves si A inverse. Okay, dun sa formula kong sinulat kanina for our solution scheme. So, tawagin ko lang A inv, yung inverse ni A. Crucial to para rin makapag-optimize kayo ng program. Kapag paulit-ulit yung kailangan yung A inverse, huwag niyong isulat na inverse A dun sa buong program. Kasi ang gagawin ni Matlab, every iteration, i-compute niya yung inverse of A. Pero it will be more efficient if you compute the inverse of A one time and then assign it to one variable. Tawagin mo siyang A inv. Para whenever you need the inverse of A, tatawagin lang ni Matlab from its memory yung A inv. Kasi otherwise, lagi niyang i-co-compute ito. Gada na lang kailangan niya yung A inverse dun sa for loop sa lines 140 to 143. Kailangan i-compute ni Matlab si inverse A. Hindi intuitive ang machines. It will only do what we ask it to do. Alright? Yun yung problema sa kanila. So kailangan sabihin mo mismo paano siya gagawin. Kasi hindi niya i-detect unless meron kang high-tech AI dun sa yung program, ano? Hindi niya i-detect na paulit-ulit kong kino-compute ang A inverse. So, pwede ko ba siyang compute in one time and store sa isang variable? Well, our basic computers cannot do that. Pero kailangan nyo nang maisip to as a programmer. Because otherwise, if you have a very huge matrix, and this was my problem when I was doing my PhD dissertation, tumatagal ng araw. Minsan nga, iiwanan ko yung computer ko o yung computer ko sa office na nagra-run ng Friday evening, tapos uuwi ako sa bahay, nagsasimulate siya sa office. Pagbalik ko ng Monday, hindi pa siya tapos. And I have to wait a couple more days to get some results. Ano? So kaya crucial nun sa akin na i-optimize yung code. Kasi otherwise, baka abutin ako ng linggo, hindi ako makagraduate. Ano? So dun sa mga mag-SP dyan using big data or using big matrices. So watch out for code optimization. Ano? Or pwede naman mag-run ka ng code optimizer. I think Matlab has a code optimizer that it will try to pinpoint some bottleneck in your program. So yeah, but that's for programming, yeah, it pays to always make your program as efficient as possible. And then now lines 140 to line 143 is basically the implementation of the backward iteration that I described in the slides kanina. So this is uinv of the jth column. We are computing for the jth column of the matrix uinv. Remember, ang promise ko kanina si uinv, siya yung maglalaman ng mga temperature profiles na ating na-retrieve. Now, the initialized value for uinv, ang may laman pa lang ay yung last column, the n+1 column, which is basically our time temperature. Okay? Pero dito, kukomputing ko na yung column mula sa kanan pa kabila. So meron na yung last. So kukomputing ko ngayon, simula kay n, column n, which is the second to the last column, magta-time step ako ng -1. So yung iteration ko kay j, mag-start siya kay n, pero it will go backward, 1 unit backward. So namaminosan si j ng isa as we go along the iteration hanggang makarating ako kay j equals 1. J equals 1 would be the temperature at time delta T. So ito yung one step before we go to the final initial condition or the final estimate for the initial condition. So si line 142, yun yung gagawin niya. Kukompute niya si U upper J. So compare niya to dun sa slides ko kanina. U upper J equals A inverse times the quantity U upper J plus 1 minus V upper J. Ito si V upper J. I should have written a different line for it, but anyway, that's fine. Kasi every time step, kailangan ko naman talaga itong computein, ano? So ito yung V upper J. And then yun yung makukuha nating estimate for the temperature at time J or time T sub J. Tapos, kukomputing ko yung relative error kasi ang kagandahan dito, alam natin yung buong temperature profile, right? Alam natin na yung solution dun sa PDE na target natin ay 10 e to the -4t sine of 2x. So since I am validating if my program works or if my solution scheme works, dalawa yung tinetest ko dito. Yung ating inversion solution, which is yung A inverse times U upper J plus 1 minus V upper J ay equal kay U upper J. Okay? At saka yung numerical stability ng program. Okay? So kaya ang gagawin ko, kukomputing ko yung relative error at every step of the way. But since we are matching vectors, so minamatch natin ay mga vectors, U upper J versus the vector obtained by plugging in the T sub J value into the actual solution. So kaya kailangan kong kunin yung L2 norm ng error o yung relative L2 error. Kaya kukunin ko yung norm ng residual. Ano yung residual? Ito yung na-compute natin from line 141. So ito yung estimate natin sa temperature profile sa time t sub j. Iko-compare ko siya dun sa actual solution. Kaya naka-minus siya dun sa 10 e to the negative 4 evaluated, 10 times e to the negative 4 times the time value times sine 2x. So pinlog in ko lang yung mga discretization points kay x dun sa true solution at the particular time value t sub j. So ang t sub j ko dito, ito yung t vals of j. Kasi yung t vals, siya yung naglalaman ng mga time steps. Tapos yung x vals, siya yung naglalaman ng mga spatial steps. Ano? So basically, this difference is the residual. Ito yung error vector. Ito ay isang vector na ang laman niya yung error dun sa temperature na estimate natin compared to the actual temperature value we expect because we know what happens in the rod for all time values. Alam natin yung function u na nag-govern sa temperature doon sa buong rod sa lahat ng time values. So kaya ko itong i-compare, kaya lang pag sinubtract ko sila, vector yung makukuha ko. The error vector. Now, pag nagko-compute kayo ng error sa comparing vectors, maganda tingnan nyo yung norm. How big? Because the norms are measures of how big a vector or a matrix is. So in this particular case, by default, I'm using the L2 norm. Okay. Kay Matlab, pag norm of a vector, ang ibibigay niya yung L2 norm ng vector na yon. So this numerator here, ibibigay niya sa atin yung L2 norm ng residual ng actual solution vector minus yung estimate vector natin. Tapos, to know how big this is relative to what we are trying to match, i-divide ko to by the norm of the actual solution. Ito naman ay nasa denominator. Ito yung size ng vector consisting of the true temperature values at the time t sub j. Ito yung size nung gusto nating i-match para at the end of the day, rel-er, okay, itong rel-er na to, this is just a number telling us around what percent yung error. Kasi mas madaling magkumuha ng insights kapag ka naka-percentage yung error. How much of how much off is our estimate relative to the size of what we are estimating. Kaya gusto ko relative error talaga. Okay. And this is, so that's the iteration step, the backward iteration step. May konting problema si Matlab kasi si Matlab ay ang kanyang, I don't know if this is weakness, ano, pero ang default ni Matlab, ang kanyang indexing ay nag-start sa 1. So, hindi katulad yata ni Python. Tama nga ba? Si Python, ang start ng indexing niya ay 0. So, pwede kang magkaroon ng 0th column o kaya 0th row sa isang list o sa isang vector. Kay Matlab, hindi. I think this is better. Mas intuitive na yung first column ay column number 1. Yung first row ay column number 1. So, hindi niya kayang magkaroon ng column 0 or row 0. So, kailangan kong computein yung initial temperature at i-assign siya sa U init or U initial ay equal dun sa A inverse times the temperature U inv at the first time step na nanggaling dun sa for loop ko kanina. Kaya gusto ko nakasave lagi yung nakasave palagi yung temperatures na solve natin. Pero yung mga temperature profiles natin, lagi sila mga column vectors. So, in-arrange ko lang sila into the matrix U inv. Tapos ito yung U to the upper, A inverse times U upper 1 minus V upper 0. Okay? So ibibigay niya sa atin yung final estimate natin para sa initial temperature. And this guy, right, etong U init, ito yung gusto kong malapit kay little f of x. Remember, si little f of x ay 10 sine of 2x. Yun yung gusto kong ma-achieve dito or gusto kong ma-recover. What should be the initial condition para after 1 second, ang temperature dun sa ating rod ay 10 e to the negative 4 sine 2x. Okay? Now, to give you an idea how the solution evolves through time, Kasi pwede kong ipakita, i-plot na lang to in a 3D space, right? Or in the 3D space, wherein one of the axis is your spatial axis, then another axis is the temporal axis. Tapos magkakaroon tayo ng z values, which will be basically the temperature values at that time. Pero minsan mahirap makita yung evolution ng solution kapag titingin ka sa isang three-dimensional object. Alright, medyo limited yung insight na nakukuha natin sa three-dimensional objects. So, isang pwedeng gawin ay, especially if you are doing something in time, tingnan natin yung evolution ng temperature through an animation in time. At yun yung ginawa ko sa line 147 hanggang sa dulo. Hindi pa to ganun ka-efficient, ano. So I just wrote this on the fly nung kailan ba? Nung Tuesday morning right before our class kasi late ko na realize maganda pala may animation, ano. So i-improve ko na lang to later pero pagtiyagaan na lang muna natin itong program na sinulat ko. Line 148 pause indicator. Ito lamang ay para malaman ko kung mag-i-insert ako ng pause within the animation. Kasi makikita nyo mamaya, hindi stable yung solution all throughout the time experiment. So mag-start tayo sa t equals 1, tapos susunod nating solution ay 1 minus delta t, tapos 1 minus 2 delta t, hanggang makarating tayo sa t equals 0. Pero hindi stable yung yung inverse problem solver natin hanggang sa dulo. Kaya naglagay ako dito ng pause indicator para yung animation ay mag-pause kapag yung susunod na error ay lalampas na ng 5%. And I will say 5% yung tolerable error ko. If the error is beyond 5%, then that means I will consider my solution to be unstable. Hindi ko na pagtitiwalaan yung time values, yung estimate ko makukuha pag lumampas na ako ng 5% yung error. Okay? Yun yung gagawin ng pause indicator. Then si line 149, gagawa na ako ng isang figure window na dito mapapaloob yung aking animation. Sanay tayo na figure lang yung sinusulat. Pero gusto ko kasi naka full screen yung figure ko. Para ma-full screen yung figure, ito yung kailangan yung ilagay na modifier dun sa figure command. So, pwede niyang i-copy paste. So, makakuha kayo ng figure na naka full screen, automatically. Hindi niyo na kailangang i-maximize yung figure window na default. Tapos, eto na yung nagpa-plot per time value. So, I will be iterating through J. So, ang ginagawa ng animation na to actually ay hindi siya high-tech na animation. Ang ginagawa niyo lang, meron kang isang figure window. Tapos, magpa-plot lang siya ng mga two-dimensional graphs ng temperature profile sa 0 to pi at every time step. So basically, ang gagawin ko lang, meron ako isang figure window, magbabago-bago lamang yung naka-display na figure, alright, at every time step. Hold on, guys. Ayaw makisama ng aking ilong today. So super runny nose. But anyway, so yun yung gagawin nito. So dahil may problema tayo sa indexing, kapag if-force ko si Matlab na yung for loop ko ay hanggang j equals 0. Okay lang yung mga for loops umabot ng j equals 0. Pwede nga mag-negative yung for loop eh. Pero gawin ko siya hanggang kay 0. Pero remember, wala tayong o dun sa matrix U inverse, wala tayong zeroth column para dun sa initial condition. Kaya may if-then statements ako dun. Kapag kasi j ay equal kay 0, nandun na tayo sa huling time step. Ang ipa-plot niya na to be our solution is U init. Okay, or the U initial na sinolve natin hiwalay dun sa for loop kanina. Pero kapag naman, si j ay hindi equal kay 0, ito yung gagawin niya. Ipa-plot niya yung true solution. Okay? So that's 10 e to the negative 4t times sine 2x over the interval 0 to L. Tapos yung line width, ibig sabihin gano'ng kakapal yung curve dun sa line. So ginawa kong 2 units yung kapal ng line dun sa graph para mas makita natin. Kasi masyadong manipis yung yung default na thickness ng line ni Matlab, ano, lalo na kung i-full screen natin siya. So gawin kong line width ay 2. Tapos on top of the plot of the actual solution, ipa-plot ko yung ating reconstruction. So at time step J, okay? So ipa-plot natin yung x values. Tapos yung yung J-th column ni matrix UINV. Kasi remember, si matrix UINV, bawat column niya ay yung temperature profile sa rod at time T sub J. So yun yung mga temperature values at time T sub J. So sila yung Y values. Ipa-plot ko siya using X values, which would be our discretization points from 0 to L. And then I hope by now it is clear ano yung pinagkaiba ng F-plot at saka plot. Si F-plot ginagamit kapag ka symbolic function yung gusto nyong i-plot. So this is a symbolic function in the variable x. Tapos ang kanyang interval of interest ay 0 to L. Pero kapag ka plot, discrete set of points ito na gusto mong i-plot tapos i-interpolate ni Matlab ano yung itsura ng curve. So basically, ito yung parang default interpolation. Yung sa mga nag-174, nagla-Lagrange interpolation si Matlab pag plot yung pinagawa nyo. Kasi the points you have, si x-vals, isa lang tong vector ng mga points, right? 0 to delta t to L minus, delta x hanggang L minus delta x. So ano yan? You will have a bunch of points here, a bunch of x values. Tapos yung uinv, remember it's a column vector. So isa yung column vector ng maraming rows, bawat row ay yung temperature sa isang x value. So basically this pair is a finite number of points. So ipa-plot ni Matlab yung mga points na yan, tapos i-connect the dots niya. Use a la interpolation. Ano? So yun yung ginagawa sa plot. Kung gusto mong points lang at wag i-connect ni Matlab yung dots, scatter yung gagamitin mo. Alright? Pero dahil ang nire-reconstruct ko ay say function f, gusto makakita ng isang continuous function as my reconstruction. So what I'll do is ask Matlab to do plot instead of scatter. Okay? Tapos lalagyan ko lang siya ng title, yung plot, ano, temperature at t equals para makita natin sa animation na saang time value na tayo. So I have the string temperature at t equals, and then here I have t sub j. Sa title, string lang yung kayang ilagay ni Matlab. Ano? So remember in 152, I hope you learned, ay hindi nga pala natin prereq ang 152, no? So may mga commands na gumagana lang for specific variable types. So halimbawa, yung title dito sa plot, mag-work lang siya kung string yung type of variable. When you say string, ano lang siya, text or characters. Hindi siya numbers, all right? Unless, pwede palang numbers, pero yung numbers treated as symbols lang. Hindi siya yung kaya mong i-operate. So kaya kailangan kong i-convert yung t-vals because t-vals is a double precision variable. Ibig sabihin, isa yung number. Tinitreat yan ni Matlab as a number, convert niya sa floating point representation, etc. So dahil yung kanyang variable type ay double precision, hindi siya tatanggapin ng title. Kasi yung title nag-work lang siya para sa string na type ng variable. So kailangan ko siyang i-convert to string, kaya meron na akong command na num to string. So i-convert niya yung isang number in whatever precision to string. Gagawin niyang string yung variable type ni t-vals. So halimbawa, ang t-vals natin ay 1/3. So i-convert yun ni Matlab into double precision into 0.33333 kung ilan man yung kanyang acceptable number of significant digits. Tapos yung 0.33333 na yun, nakatag yun kay Matlab na, oy, number ka. Double precision yung variable type mo. So hindi siya tatanggapin dun sa title command. So para matanggap siya sa title command, i-convert ko yung number na yon to a string. So yung 0.3333, hindi na ngayon iti-treat ni Matlab to be a number. Iti-treat niya na yon as a string of characters. Alright? Para lang malagay ko siya sa title. Tapos font size, para mapalaki ko yung font size. Kasi designed yung laki ng title for the small default figure window. Tapos remember, finull screen ko yung animation, so dapat lalakihan ko rin yung font size, ano? Tapos nilagyan ko ng subtitle yung ating figure. Yung subtitle niya ay yung relative error naman. So para rin makita natin yung accuracy at every time step dun sa animation, ilalagay ko sa subtitle ano yung relative error. Okay? Tapos naglagay ako ng legend para malaman natin aling graph yung exact solution at anong graph yung estimate. Okay? Tapos X label lang para magkaroon ng X yung x-axis. Tapos etong get frame, sinisave ni Matlab yung bawat frame ng animation. Alright? So basically, an animation is just a huge number of consecutive figures. Ano? So, ganun din yung ginagawa niya dito. Kinukuha niya yung bawat frame ng animation, isa-save niya sa matrix MM o sa structure MM. Para mamaya or para later, pwede kong ma-save yung animation into a GIF or into an AVI or an MP4 file. Although, hindi ko pa siya nagagawa. Hindi ko ma-figure out yung tamang frame rate para dun sa video. Nagrereklamo si Matlab. So siguro, next time ko na lang idadagdag yung line para ma-save nyo into a GIF or into a movie or into an MP4 file, yung animation na makukuha natin. Inisip ko pa kung paano ko nga ba siya ginawa dati. Kasi nagdedepende rin to sa frame rate eh. Pero naka-ready na to. Naka-save na yung frames kay MM. Kailangan ko lang tingnan kung ano yung tamang parameters sa frame rate and so on. Titingnan ko rin yung documentation ni Matlab sa pag-save ng animation para hindi na natin i-play ng paulit-ulit yung i-run paulit-ulit yung program just to see the animation. Because once you run the simulation, you have the frames in the animation saved in the structure MM. We could have just saved it as a video or as a movie and then played the movie using your movie player. Ano? So, pero next time na lang siguro yun. Hinahanap ko pa yung code at saka yung parameters para sa kanya. Kasi yung usual na save as movie or save as animation, ayaw gumana eh. Nagrereklamo siya sa frame rate. Pero I'll figure it out later. So, sinisave niya dito sa line 166 bawat frames. Tapos sa line 167, draw now, sinasabi lang nito kay Matlab, i-drawing mo na yung frame. Okay, so yung bawat frame, ilalabas niya into the animation. Pero nilagyan ko siya ng pause na 0.1 second per animation. So, di ba different frames yan? So, ginawa ko ay medyo may maiksing pause between two animations. Kasi otherwise, pag walang pause yan, or kung mataas yung value ni pause, ang haba naman ng pause. Alright, so ito yung nagsasabi kung gaano katagal yung pause. Parang nakita natin last time sa forward animation, ang haba ng 0.1 na pause. Siguro here, let's make it smaller. Gawin natin yung pause ay 0.05 seconds. Para mas mabilis yung animation. So yung pagdodraw niya ng one frame after the other, mas maliit yung delay. Tapos ito yung sa pause indicator natin kanina. So, ito yung sinasabi ko kanina na kapag yung relative error, look at the if statement. So, pag yung relative error ay lampas na ng 5% at naka-on yung pause indicator. Pag ang pause indicator ay 1, tapos ang relative error ay greater than 5%, then ang gagawin ni Matlab, ititigil niya yung animation. Okay. So, magpo-pause yung animation, magple-play lang siya ulit pag pumindot kayo ng any key on the keyboard. So makita nyo mamaya magpo-pause yung animation kasi that's the signal na after that frame, yung susunod nating result ay is greater than 5% na yung error. Para alam natin kailan tumigil ang pagiging stable ng ating solution. Tapos I save some of the parameters here. Stable T, ito yung nagsasabi sa atin anong time step, yung huling time step kung saan siya naging stable. Para alam natin na after or any time value na mas maliit sa t-vals of j, hindi na stable yung solution. Tapos here, line 173, binilang ko lang ilang steps yung naging stable. Or nakailang backward iteration tayo before naging unstable yung ating iteration. Tapos para hindi siya paulit-ulit na nagpo-pause, kada lumalampas ng 5% yung error because I only want to pause at the first time that the relative error goes beyond 5%, ni-reset ko na yung pause indicator ay in-off ko na sa line 174. Okay? And then I think that's it. And then lines 180 to 184 gives us the final reconstruction. Ito yung makukuha natin na initial condition o temperature on the rod at time t equals 0 at the end of the animation or after the end of the simulation. All right. So that's the code. And then let me run it and let's see how it goes. So I think okay naman lahat. So I'll press F5 para mag-run yung program. Bakit siya matagal? Hindi ko alam. Baka yung computer ko ay nagbabagal ngayong araw. Okay, there we go. The animation opens up now. So I hope you're seeing it. Okay, sorry. Kailangan mag-init ng machine ko. Yan, nagsimula na siya mag-move. So we're moving backwards. So 0.9, 0.899 times, 0.87. Tapos tingnan niyo yung relative error. Yung relative error pataas siya ng pataas, right? Now we're below 1%. Now we are at 1%. Tapos nakikita niyo yung dynamics nung temperature na nare-reconstruct natin. Mukhang okay pa siya, no? Nagbabago yan, di lang halata. Tingnan niyo yung scale dun sa y-axis. Nagbabago yung scale. Kasi yung solutions natin ay 10 e to the negative 40 times sine 2x. So basically, it's sine 2x times a constant. So kaya medyo lumalaki at lumiliit lang yung graph. Pero sine function pa rin from 0 to 2 pi. Masyado pala mabilis yung animation kaysa dun sa gusto kong sabihin. Ano? Pero now, you see that the animation now paused. Nag-pause na siya at t equals 0.38. So ibig sabihin na reconstruct natin yung temperature. So ang data natin ay temperature after 1 second. Tapos nag-work tayo backwards in time para makuha yung initial temperature. Okay? Now, at time t equals 0.3844, so nandiyan tayo sa 3844 na yan. Ito na yung nakuha natin na temperature, which is good because the relative error is just 4.6%. Okay, 4.6% pa lang yung relative error. Tapos tingnan nyo, medyo maganda yung temperature na nakuha natin, right? Medyo ano nga lang siya, hindi nga lang siya smooth kasi may mga sudden turns or may mga cusp siya. Pero anyway, this is the best that we can do kasi remember, nag-discretize tayo. Now, tumigil siya kasi remember dun sa ating program, naglagay ako ng pause. Sabi ko kay Matlab, i-pause mo yung animation kapag ka yung susunod na relative error ay lalampas na ng 5%. So that's the cue for me not to trust the reconstruction anymore. All right? So nandito, nasa time 0.38 tayo, I can accept this as my solution. Because this is about 4 point, what? This is about 0. 4.6% na yung relative error, which is still fine for me. Kung medyo mataas yung iyong error threshold, edi gawin mo yung pause when the error goes beyond 1%. Kung napaka-accurate dapat ng gusto mong results. Pero say for real life application, siguro an error of about 5% is still good. Okay? Yung iba nga hanggang 10% accepted nila. Unless medical yung application na gusto mong isolve. So baka gusto mo mas mataas yung relative error. Pero for engineering, pwede pa nga sa kanila yung hanggang 10% eh. So pero tayo mga mathematician, medyo shook ako nung nagpi-PhD. Kasi natuto ako na sa math, ang relative error na gusto natin, mga 10 to the minus 3, 10 to the minus 6, etc. Super liit. Kasi gusto natin almost exact lahat. Pero when you go to practical applications, they accept na hindi naman ganon lagi ka-perfect yung mga solution schemes. And we don't need to be that accurate. So kaya nga sa engineering, nung sinabihan ako nung prof ko na, okay na yan, 10% yung relative error, that's acceptable. Then sabi, napaisip na lang ako, grabe, buti pa sa applications, pumapayag na 10% yung error. Pero sa math, ang laki nun para sa atin, Gusto natin 10 to the minus 3, 10 to the minus 6 yung error. So, but anyway, yeah, this is the cue that all other results beyond 0.38 second ay hindi natin kayang i-trust kasi lampas na ng 5% yung ating relative error. Maybe I can say something about this later, pero let's just continue the animation. So nag-pause siya para mag-continue yung animation. You just need to press any key or space. Try ko ang any key. Alam ko space gumagana, pero yeah, gumagana kahit anong key. So makita nyo, nag-fall apart na yung ating process. Kasi ang laki na ng relative error. So now we are at 7,200%. Yeah, ang laki na ng relative error. And look at the scale of the temperature, the y-axis. It's times 10 to the 5th. Now it's to the 6th, to the 7th, etc. And which is very far off from what we expect because what we're trying to reconstruct is what? 10, ano nga yung nire-reconstruct natin? 10 sine 2x, which is magnitude 10, right? Pero yung magnitude nitong ating final reconstruction ay 10 to the 9. Makikita nyo yung actual solution, siya yung blue line, which is almost flat. It will be almost flat kasi nga ang usapan natin, ang nire-reconstruct natin, ang exact solution dun sa inverse problem ay 10 sine 2x. So dapat from negative 10 to 10 lang yung axis ng temperature, pero ngayon nasa 10 to the 9 tayo. Ibig sabihin, ang laki ng blow up nung ating reconstruction because unstable yung ating solver. Okay? After some time steps. So if you want, you can maximize on a particular portion of your graph. So kung mag-maximize ako dyan, mag-zoom in lang ako para makita natin na curve pa rin yung solution, yung blue line. So hindi ko pala siya mapapakita kasi pag nag-zoom in ako, lumiliit na yung scale sa x-axis pero lumiliit din yung scale sa lumiliit yung scale sa y-axis, lumiliit din yung scale sa x-axis. Basically kahit anong curve yan pag nag-zoom in ka para kang straight line. So pero anyway, yeah. So that's the problem with this solution scheme. Hindi siya ganun ka-stable, especially for huge amount of steps backward. Pero let's revisit what we have. Balikan natin yung solution natin dito. Okay. Now, let me see. Hindi ko kita yung buong screen ko. Siguro, yeah, there we go. Tingnan natin yung stable T. Yung stable T, kinompute ko to kanina, no? Stable T. So, itong stable T, what? Little t. 0.3884. So, ibig sabihin, na-reconstruct lang natin to certain accuracy yung temperature hanggang 0.38. So, starting from t equals 1 hanggang 0.38, maganda yung reconstruction natin. How many steps were we able to accomplish here? Stable steps. Naka 74 steps backward tayo. So, it took 74 steps backward in time. Simula kay 1, papunta kay 0.38. We took 74 iterations, 74 calculations without anything breaking down. So, naka 74 steps naman pala tayo, which is, I think, which is still good. All right? Though ang temporal discretization natin ay 120 steps. So, meaning, 74 out of the expected 120 steps ay okay yung pag-run ng ating algorithm. So basically, if you want to implement this using other methods based on this benchmark test, you can say na, sige, pwede ko pala itong gawin. Either magba-backward solution ako ng 74 steps o kaya aabot lang ako hanggang 0.38 seconds. So yun yung pwede nyo isipin na kapag gusto nyo gamitin yung code for a specific real-life problem na hindi nyo na alam yung exact solution, so hindi kayo makakompute ng relative error, so pwede nyo gamitin tong benchmark results natin na baka naman 74 steps yung magic number. So pwede niyong i-run yung inyong simulation using your measured data 74 steps backward. Kasi itong benchmark test natin, okay siya hanggang 74 steps backward. So baka naman, kapag ka in-apply ko siya sa real life scenarios, maging stable pa rin siya after 74 time steps. So hindi nyo tatapusin yung buong 120 time steps hanggang makarating kayo kay zero. Kasi alam na natin na hindi siya stable. So if you don't have any idea of what your solution is or the desired solution is, then gamitin nyo tong results ng benchmark test. Of course, there's no proof that that will happen. Base lang siya sa isang experiment. So if you want to get a better number, i-run nyo tong simulation with different known scenarios. Hanap kayo sa literature. Ano pa nga ba yung solutions ng heat equation? Ano yung constants? Ano yung initial condition? Ano yung boundary condition? Tapos i-validate nyo itong ating program using those exact solutions. Tapos tingnan nyo ilang stable time steps yung kaya nyong gawin. Tapos i-average nyo yung stable time steps na yon, or kunin nyo lamang yung minimum para alam nyo na ano yung worst case. Ilang beses kayo pwedeng mag-iterate na makakakuha kayo ng solution that you can trust. All right? Excuse me again. All right. So, yon. Or another thing that you can watch out for is look at this value of stable t. Sabihin nyo, kaya ko lang i-construct simula 1 second hanggang 0.38. Kasi baka naman, pag lumampas na ako ng 38 second, ay hindi na stable yung result. So these are some things that you can think about when implementing the method. Benchmark lang naman to. There's no proof to it. It's simply ad hoc. Lalo na kung wala kang idea, you'll be shooting in the dark. But at least here, magkakaroon ka ng konting idea. Ilang time steps, naging stable siya in one of our experiments. And baka naman, lalo na kung similar naman yung boundary conditions, baka naman, ganito rin ka-stable kapag ka in-apply ko na siya sa ibang real world, sa ibang real life applications. All right? Now, ano yung gusto? Okay, but this is for exact data, right? Yung right-hand side natin, yung initial condition, basically the terminal value that we used as the data to this inverse problem is perfect, right? And evaluate ko lang yung true solution at time t equals 1. Remember here in line 132, true data yung ginamit natin. True data would be, in-evaluate ko lang yung true solution at time t equals 1. Tapos yun yung ginamit kong initial condition dun sa iteration. Okay? Para makabalik tayo dun sa function little f. Pero anong mangyayari pag nilagyan ko na siya ng noise? Which is basically something that you need to look at whenever working with real life data, no? Lalo na kung alam mo sa lab ganito yung gagawin ko. Magme-measure ako ng temperature. Pero wala namang perfect thermometer, So kahit napaka-fancy nung iyong thermometer, laging may error doon sa makukuha mong temperature. So we want to factor in the uncertainty in the measurements. Kailan lang ba tayo nagkakaroon ng true data sa inverse problems? Kapag nagkakaroon ka lang ng perfect data kapag ito yung target temperature mo. Halimbawa, ang interpretation dito sa sinosolve nating inverse problem ay gusto kong temperature after 1 second ay 10 sine 2x. Or sorry, 10 e to the negative 4 sine 2x. Siya yung gusto kong ma-achieve na temperature after 1 second. The question posed is, ano dapat yung temperature na ilagay ko ngayon dun sa rod para after 1 second, ang temperature niya na ay 10 e to the negative 4 sine 2x. Well, that's the perfect data. That's one time that you have a perfect data, lalo na sa aircon. Pag sinabi niyo sa aircon niyo na gusto ko ang temperature ay mag-stabilize sa 23 degrees Celsius. Now, kukompute ng inyong aircon, especially if you have automatic climate control, So kapag may ACC yung iyong aircon, kukompute ni aircon gaano dapat yung pagbuga ko ng cool air para yung temperature dun sa room ay mag-stabilize sa 23 degrees Celsius. Ganun yung nangyayari sa computer box ng mga aircon na merong automatic climate control. So, in-regulate niya yung paglalabas niya ng cool air para ma-achieve yung temperature na gusto mo in the long run. So, nagsosolve siya ng inverse problem within the mechanism of or within the computer box of the aircon. So, kapag ka ganun, then you have a perfect data. That's fine. You don't have to take care of noise. Pero actually, kailangan mo pa rin kasi ill-posed nga or ill-conditioned ang inverse problems. Pero in real-life applications, kung mini-measure mo yung data, right? That data that you want to use in your inverse problem is measured, then pag nag-run ka ng or nag-validate ka ng program o ng numerical framework mo, dapat i-consider mo yung noise. Yun yung ginagawa natin dito. Nagdadagdag tayo ng Gaussian noise dun sa true data, right? So, i-comment ko lang itong noise kasi itong noise equals 0 kasi papalitan ko na ngayon yung noise and comment ko yung lines 134 to 135. Itong lines 134 to 135, ito yung, ito yung nagko-compute or ito yung nag-generate ng noise vector. Okay? So in line 134, I'm just initializing the noise to be a vector the same size as x vals, pero naka-transpose. Kasi yung x vals natin ay row vector, pero everything here should be a column vector. Kaya may apostrophe pa yan. Hindi ako consistent kasi sa pagka-create ng mga vectors. Probably next time I'll make them uniform. Pero para yung noise natin, yung noise vector will be the same size as x vals. Okay? So para maging column vector siya, so ganito yung gagawin ko. So I'm creating a random vector na ang size niya, ang input kay rand, ay ano yung size? Gaano kalaki yung random vector na gusto mo or yung random matrix na gusto mo? You can write rand of 1, 3, bibigyan kanya ng matrix na 1 by 3 na ang laman ay uniformly distributed random numbers between 0 and 1. So line 134 will generate a vector or a matrix of random numbers that is uniformly distributed from 0 to 1 of the same size as x vals or x vals transpose. So, yon, magkakaroon tayo ng random vector na ang laman ay from 0 to 1. Pero ang gusto kong size ng error, nung noise, ay say 1% noong true data. So I think nabanggit ko na to, and I hope this is what you used in your in one of the previous homeworks. So i-scale ko ngayon yung noise vector. Kasi hindi ko alam kung gaano kalaki yung noise vector. Ang alam ko lang, si noise vector, ang laman niya ay mga numbers from 0 to 1, okay? Na uniformly distributed random numbers na ang size ay kaparehas ni x vals. Pero hindi ko alam kung gaano siya kalaki. So i-scale ko siya by this factor. Okay, that's 0.01 times the norm of the true data divided by the norm of the original noise para sure ako na ang size na ni noise ay 1%. Okay, so pwede niyong palitan itong 0.01 by the percentage size of the noise that you want o yung relative size ng noise. Kung gusto niyo 5% yung noise para imimik niya yung measurement data, so gawin niyo itong 0.05. If you want little noise, kasi alam nyo na napakaganda ng thermometer nyo na ginamit para i-measure yung real-life data, then paliitin nyo tong noise, itong 0.01. Pero ang gawin nating default sa atin ay 1% kunwari yung noise. Kaya may 0.01 yan. Tapos si uinv, so ito yung initial data natin ay gagawin kong true data plus noise. So ito na yung true data B plus noise vector epsilon. Tapos ito yung isa-solve natin. Right? Tapos tingnan natin gaano ka-accurate or kailan magiging stable or hanggang saan magiging stable yung ating solution. Remember, when we use perfect data, umabot tayo ng 0.38 second without the relative error going beyond 5%. So yun yung kino-consider natin na stable hanggang 0.38 seconds or we got 74 time steps na stable yung solution. Tingnan natin ay yung magiging epekto ng 1% noise. dun sa ating simulation. So I'll hit enter, I'll hit F5 now para mag-run yung animation. Pinapahiya ako ng laptop ko ngayon. Alright? Ang bagal niya mag-run. Okay, patience. Pero nauubos ng patience ko sa laptop. Pero anyway, oops. And there you go, nag-crash na si Matlab. Lalo pa niya akong pinahiya. Buksan ko lang ulit. Grabe. Siguro nagalit siya kasi inaaway ko siya. Pero anyway. Antayin lang natin. So, nagbubukas na si Matlab. Pero sana hindi ito pagpaparamdam ni computer na kailangan niya na mag-retire. Ano? Hindi ko pa afford ang bagong laptop. Pero simula nung nag-update ako sa 22B, sa Matlab 22B, medyo bumabagal yung ano ko, yung paggamit ko ng graphics. Katulad niya, nag-hang pa yung pag-load ni Matlab. When I was using Matlab 2020, okay pa naman siya. So dapat siguro hindi muna ako nag-update kay 2022B. How about you guys? Anong gamit yung Matlab? Kasi ang yabang ko na dati na super bilis ng computer ko. Pero ngayon, kay 22B, medyo nag-fail siya. Okay, run ko ulit. Ito, hopefully na-save yung paglalagay natin ng error. Ng noise. There you go. Alam ko na. Dapat iset ko na OpenGL yung ginagamit ko na graphics accelerator. But anyway. Okay, there you go. So ito na yung noisy data yung sinasimulate natin. Okay, so good. Okay pa. Pero ang aga, tingnan nyo, 3% kagad yung error. Tapos ito, tumigil na siya. At 0.94 seconds, nasa 4% na kagad yung error. Okay? And this is how the 1% noise really affected our solution. Before, kaya nating magantay hanggang 0.38 bago maging unstable yung solution natin or bago lumampas ng 5% yung relative error. But now, look at this. We just took some time steps, nakaabot lang tayo sa 0.94 second, tas yung relative error 4.48% na. And right after this, if I hit any key, yung relative error lalampas na ng 5%. So nakita nyo, 6% kagad. Nasa 10% na ako, hindi pa nakakalampas ng 0.9 second. And you see how fast the estimate diverges with respect to the actual solution. Ganon ka-unstable yung inverse problem solver natin. So, yeah, antayin lang natin. So, the next question is, which will be the focus of the next few sections of the course is, how do we combat etong instabilities caused about by the naive reconstruction? Because here we're just using the inverse, the actual inverse of the linear system. All right? Meron bang paraan so na kaya nating i-combat yung instability brought about by a seemingly naive and exact solution on paper? Right? Kasi yung ginawa natin, meron tayong equation na A, matrix A times U upper J plus V upper J equals U upper J plus 1. Tapos sinolve ko lang naman from there si U upper J in terms of U upper J plus 1 and and V upper J. Alright? So on paper, exact yung ginawa natin. Wala tayong violate. Ginamit natin lahat ng laws of algebra, laws of differential equations, etc. We had been very careful when we designed our solution. We did everything on paper. Pero yung ginawa nating solution on paper, meron pa pala siyang inherent theoretical error, which came from the fact that our forward operator, yung ating forward linear operator, is an approximation of the forward problem. So ginamit natin yung approximation ng forward problem para magkaroon ng solution dun sa forward solver. Wala tayong naging problema sa forward solver. Pero nung ginamit natin yung model natin for the forward problem to come up with a solution for the inverse problem, doon na nagkaroon ng problema. All right? And that is basically what causes the instability of our solution. In fact, here, yung final reconstruction natin, umabot ng order 10 to the 22nd. Kanina times 10 to the 9th lang, ang sama na ng loob natin, right? Ngayon, umabot ng times 10 to the 22 yung ating solution, which is very far off from the order 10 to the 1st na hinahanap natin to be the actual solution. Okay? And then if we revisit the statistics here, balik ako kay Matlab, tingnan natin yung stable T. Ito, naging stable lang siya. Sabi nga natin kanina hanggang 0.94 second. That's a big jump from 0.38, which we got from the real world data, from the true data or the exact data. Tapos ilang steps ang kinaya natin? We just had 7 steps backward in time bago nag-fall apart yung ating method. Right? Kanina dun sa perfect data, we afforded 74 steps. Now, hanggang 7 lang, unstable na yung solution. Right? So, tingnan natin kung palitin natin. Baka masyadong malaki yung 1% na noise. Siguro gawin natin 0.01% yung noise. Nagdagdag ako ng 2 zero sa noise. So, mas maliit yung noise kung ilalagay. Tingnan natin kung gaano makakailang time steps tayo. So remember, sa true data, naka 74 stable steps tayo. Sa 1% noise, naka 7 stable steps lang tayo. Tingnan natin sa 0.01% na noise, kung makakailang stable steps tayo. Sana hindi siya mag-crash. Okay, there you go. Okay. Seems nice. Nasa 0.3% pa lang yung relative error. 0.5%. Naka 1% relative error na tayo. 4% error. Inabot tayo ng 0.85124. So, medyo lumaki. Dumami yung time steps natin kanina hanggang 0.94 lang. Pero ngayon, naka na tayo, 0.85. But if you think about it, we lessen the noise by 100 times. Kasi dinivide natin by 100 yung size ng noise. Pero that only afforded us probably a couple dozen time steps from 0.94, nakarating tayo ng 0.85. Eto, napakaliit na nung noise. So if you will contextualize it in a lab, so para makakuha tayo ng siguro mga 10 or 20 more stable time steps, dapat super accurate ng ating measurement device. Dapat 100 times more accurate. Pero is that worth it? Minsan hindi siya worth it. Kasi konti lang yung nadagdag na time steps, kinailangan mo ng napaka-accurate na measuring device. In fact, in this simulation, this is 100 times more accurate than what we simulated in the previous experiment. At minsan, wala tayong access sa ganung ka-accurate na measuring devices. So kaya tayong mga mathematicians, dito tayo papasok ngayon. Kailangan nating mag-imbento ng method na hindi kakailanganin ng mga applied scientists ng super expensive, na super accurate measuring devices. So you see how powerful math is, na ito yung problema ng mga halimbawa biologists or physicists, kailangan nila ng napaka-taas na napaka-accurate na measurements. So kailangan nila ng equipment na napakamahal. Tayong mga mathematicians, sabi natin na hold on on your money first. Let's try to see if we can devise a solution to combat this instability. And all we need would be pen and paper plus our brilliant minds to come up with a nice strategy to combat the instability. Hindi natin kailangan bumili kagad ng super accurate na measuring devices. All right? And that's the promise of the next few sections of the course, wherein we'll try to look at how can we combat the instability brought about by noise in the data in the solution to an inverse problem. Okay? And I guess this is a good time to stop. Now, kanina in the backstage, I was talking about the possible second problem set. Ano? So the second problem set, actually para nagdalawang isip na ako. Because I was thinking kanina, during the class, siguro tatlong problem sets tayo. But I think okay lang ba sa inyo na 2 problem sets na lang? So meaning we have 1 problem set left before your final project para hindi na masyadong para hindi na masyadong marami kayong gagawin sa 191 ano. Kasi gusto ko sana tong 191 chill lang para magkaroon kayo ng experience. Lalo na dun sa mga SP advices ko dito na ganito yung gagawin nyo sa SP ano. Para meron na kayong konting idea kung ano yung gagawin nyo para pag nag-SP kayo, konti na lang yung aaralin nyo on your own. Ang daya ko eh. Ginamit ko talaga yung position ko para sabihin, mag-request sa math division na magtuturo po ako ng 191. And that's for the benefit of my advicees para 3 units kagad yung makukuha nila sa pag-aaral nung kailangan nilang gamitin para sa SP. Unlike kung sa SP pa nila pag-aaralan, it would be additional work for them. Okay? Pero yeah, kaya pinilit ko kayo na ngayon kayo mag-take kasi usually ganito yung mentality ng mga nag-o-offer ng 191. So kaya hindi ako pwede lagi ang nagtuturo ng 191 kasi dapat paiba-iba yung topic na nasa 191. But anyway, so that's it. So sige, ganun na lang. Probably para maplano nyo, nasa week 10 na tayo, no? So probably there would be 5 more weeks or 6 more weeks in the semester. So siguro I'll give the second problem set maybe 2 or 3 weeks from now. Ito yung ang gagawin niyo sa problem set na yon ay siguro ito na ring heat diffusion o kaya yung convolution. Tapos gagamit kayo ng regularization, which would be our starting topic for next week. Tapos, papakita nyo lang na na-combat na natin yung instability nung inverse problem by just adding another layer to our solution. Magkakaroon tayo ng regularization routine. Dun sa mga nag-take ng 175 last semester, ito yung L-curve regularization technique na diniscuss natin briefly. So we'll rediscuss it here. So kung alam nyo na yung L-curve, you can skip those classes. Pero gusto kong idagdag pa rin yung Morozov Morozov discrepancy principle, which is basically an optimization problem para makuha si alpha. Para dun sa mga applied math dyan, optimization yung forte, makarelate kayo ng konti. Kasi isa rin siya magandang special problem or thesis, how to find that optimal alpha in the regularization procedure. Yung ginagamit ko ngayon ay napaka-primitive. Ginagamit ko ay Newton method, which might be outdated. For you guys majoring in optimization, you might have a better solution in mind. But that would be it. And then we'll have the final project as the final requirement for the course, aside from the scattered homeworks all throughout the weeks. Pero siguro yung final project ay during the final week nyo na kailangang ipasa. So that you have spoiler ako eh. So you have the Christmas break to work on it a little bit, Tama nga ba? Final week natin ay January pa, no? So parang you can spare probably 2 to 5 days ng bakasyon para gumawa ng project. All right. Pero you can also do it earlier so that you don't have to work over the Christmas break. And you can work in groups again, para hindi na ganon kabigat sa inyo yung final project. Okay? So yeah, you can talk among yourselves if you have a specific PD in mind and you want to have some classmates to work with you para mas magaan yung work, then you can do so. Pag-isipan ko kung ilang members, okay? Oh, yes, Ned, you have a question?
Sir, doon po ba sa final project, like need pa rin po ng parang soron na documentation ng code or like pwede pong or code lang po ba siya in a way?
Ano siya, kailangan ng write-up because I am more on the write-up or the presentation rather than the code. Kasi yung code naman, pwede niyo siyang i-download kung saan or pwede niyo gamitin yung code na pinersend ko, i-ano niyo lang, i-modify niyo lang. So that's fine. But I'm more into the narrative. Gusto kong makita yung ano yung problem na sinolve nyo, ikwento nyo ng konti, ano yung motivation, why you chose that particular problem, and then kwento nyo lang ano yung methodology. Sir, nag-download po ako ng program mula sa GitHub, tapos minodify ko lang po siya ng konti, ginamit ko yung data mula dun sa application area ko, and boom, ito na po yung nakuha kong results. Tapos say something about your results, ano yung significance ng results nyo or contextualize it back to the practical application that you had in mind in the beginning. And then that's it. Hindi ako super technical dun sa problem. No? Dun sa project. Gusto ko lang makita na na-apply nyo yung mga natutunan nyo dito sa course in a particular area. All right? And not necessarily a program. Siguro, ano bang gusto nyo? Written output o video presentation output na lang? Maybe either would be fine with me. So kung magaling kayong magsulat ng scientific paper, then you can submit it in a written form. Or kung mas feel nyo na mag-present and you want to practice your presentation oral skills, then submit a video recording. All right. More on the project later as we go along. Pinag-isipan ko pa rin yung mechanics. Pero you can start talking among yourselves. Hoy, ano yung gusto mong project? Oh, medyo related yan. Interested din ako dyan. Then probably you can collaborate and work on a single project. Okay? So para hindi ganon kabigat sa inyo. Pero I will think about how many members in a group yung pwedeng mag-work. Or if you want to work solo, it's up to you. Ano, you have all the options. We can be as flexible as possible in the course. Okay? So other questions? Other concerns? Okay, so if there are none, thank you guys for coming today. Again, homework number 5 is due right before our session on Tuesday. Enjoy the weekend, and until then, guys, keep safe. Bye-bye.
Thank you po, sir.
All right, welcome.
Thank you po, sir.
All right.